Hello, everybody. So hopefully you took your second test. I was looking at the grades. They looked pretty good. I did have one or two people reach out and say, oh my goodness, the tests, it feels like I don't have enough time. That is why you need to study. So sometimes when we have an open book exam, we leave more to the day of the exam than maybe we should, right? So what I would say is if you're feeling like the tests are, like you're not having enough time, you probably are going to want to be studying a little bit more so you're not having to reference so much. That would be my best bet. That would be the best bet. But overall, they looked pretty good. So keep up the good work. We're going to move into chapter 5 today, which is thermochemistry. The next exam, which is like in 4 weeks from your last exam, so 4 weeks from the weekend, is going to cover thermochemistry and then electrons. So we've got some time to sort of casually go through these chapters. So I switched up the slides. I'm using an older set of slides because I just feel like they're simpler. The slides that they're still from the same textbook chain. They're just from an older edition. I just feel like they're a little bit simpler and more accessible than the newer slides, which just felt like a little bit more complicated than maybe we needed to get into. So keep it simple when we can. Okay, so chapter 5 is all on thermochemistry. Pretty much this whole chapter is going to be looking at energy. The first part of the chapter is really more concept-based stuff, energy increasing, energy decreasing. Later on in the chapter, we get into a lot more calculations. So let's try and get through some of the concept stuff. So energy, so our ability to do work or to transfer heat, and that's really like our internal energy. When we're talking about an object's internal energy, how much energy it has, it's its ability to perform work or to transfer heat to the surrounding environments. And when I'm talking about work, I mean energy used to cause an object that has to have mass in order to move. So if I have a big rock and I want to push it along the ground, I have to do work, and not just work in the loose sense of, oh, it's work, it hurts my muscles, but work in the sense of physics and chemistry, where it's a force over a distance. Work is based off of how big the object is and how quickly the object is moving, right? So if the object is really small, I don't need to use as much work. If the object is much larger, it's going to require a lot more work or energy. Heat is another type of energy. This is the energy used to cause the temperature of an object to rise. So when I pump heat into an object, I will increase its temperature. And when we're talking about temperature, we mean pretty much the kinetic energy of the molecules or the vibrational energy of the molecules. Again, this is also dependent on how much of the object you have, and it's also based off of the chemical makeup of the object. So certain objects have higher heat capacities, and we'll get into that a little bit later, but it just requires more energy to heat it up. Like for instance, water requires a lot of heat to change its temperature versus silicon or silicates like sand. So that's why you'll find milder climates along the coastlines, because the water kind of acts as a buffer. So with energy, we can kind of divide it into two different things. We've got this little guy on a bike here. Potential energy. So potential energy is energy that an object holds within it based off of its position or its chemical composition. So potential energy is energy that hasn't really been used yet. It's sort of being stored in the object. This gentleman over here on the bike has a certain amount of potential energy because he's at the top of a hill. He's not moving yet. Let's say he's just kind of looking down at the hill. Oh, do you think I can make it? I think I can do it. I think I'm going to do it. Okay, I'm going to go down this hill. And it required him, he had to somehow get up to the top of that hill, right? So he did have to exert energy to get up to the top of this hill to create that potential energy or that energy based off position. How did he get up to the top of the hill? Maybe he rode his bike to the top of the hill. Maybe he drove his car to the top of the hill and he's just going to go down the hill instead. The guy over here on the right, once he's sort of moved over or crested over the edge of this hill, is in a state of motion. Sorry about that. And when you're in a state of motion, you possess a certain amount of energy, which is known as kinetic energy. So he's taken this potential energy of sitting up at the top of the hill, and he's now converted it into kinetic energy. And you do want to know this equation. Kinetic energy is going to be equal to 1/2 mv squared. And m is mass, and it's specifically mass in units of kilograms. Okay, so when we're using this equation, we want to have that in kilograms. V is equal to our velocity. And this is going to be in meters per second. And you want to notice that this is a squared value, right? So the squared is just talking about the V. It's not talking about the M. We don't square the M. So if you're ever going to be solving for kinetic energy, just make sure that your units are matching up with kilograms and meters and seconds. So the unit for kinetic energy, if I plug these in, should end up being my mass is kilogram. My volume is meter per second, but it's squared. So it should be meters squared per second squared. So it's kind of a funky set of units. Kilograms times meter squared divided by second squared. You can see that on the next page, that those in fact are a unit of energy. So we've got the kilogram times the meter squared over the second squared. And this is sort of mouthy and wordy and difficult to write. So we can actually reference one of these as a joule. And you've probably heard of a joule before. Energy is measured in joule. So the joule, which is named after James Joule, is equal. It's a 1-to-1 ratio between these two things. Sometimes you'll hear the unit of a kilojoule. So 1 kilojoule is equal to probably just what you're thinking, 1,000 joules. So the SI unit is the joule. We can apply prefixes to that as well. Just like we can apply prefixes to meters and grams, we can do it to joules. An older unit that we still use today quite often is the calorie. And 1 calorie is equal to 4.184 joules. Now, when this is talking about a calorie, this is a little c calorie. That's not a nutritional calorie, okay? When we're talking about food or a nutritional calorie, that's sometimes called the big C calorie or the kilocalorie. So 1 big C calorie is equal to 1 nutritional calorie. Or sometimes it's called a kilocalorie, and it's equal to 1,000 little c calories. Okay, so 1 big C calorie is equal to 1,000 of these little c calories. So when we're talking about this here, we're talking about a small amount of a nutritional calorie, 1,000th of a nutritional calorie. So just for practice, let's say I've got a candy bar. Okay. And it has 312 big C calories or nutritional calories. I want you to tell me how many joules that is. So you're given that you have 312 big C calories. I want you to find how many joules that is. Turn my mute off. This is just a basic conversion problem. So I start with my given information, which is 312 big C calories. So using dimensional analysis, the first thing I'm going to do is go from my big C calorie into my little c calorie, because my relationship between joule is with little c calorie, not with big C calorie. So I'm going to take my given information and I'm going to convert it to, so big C calorie, for every 1 big C calorie, I get 1,000 of these little c calories. And then for every 1 little c calorie, I can use this thing right here, we get 4.184 joules. The little calories will cancel, the big calories will cancel, and I end up with quite a large number. I have 3 sig figs, so I'm going to go with 1.31 times 10 to the 6 joules, or 1,310,000 joules. Quite a bit of joules packed into that candy bar. Okay, so let's go to the previous slide and play around with that equation now that we've got a little better grasp of the units. So we've got kinetic energy equals 1/2 mv squared. Again, m, we like that to be as a kilogram, and v, we want to have as meters per second. So I've got a couple practice problems set up. I'll do the first one here. So find the kinetic energy in joules of a biker with a mass of 95 kilograms moving at 15 meters per second. I'm going to try and set that one up. I'll give you all another 30 seconds or so. At least get it set up. So kinetic energy, we know from that equation, is equal to 1/2 mv squared. We need a value for mass, which we have here, and we need a value for velocity, which we have here. And fortunately, these are both in the units that we like. So we have kilograms and we have meters per second. So all we really need to do in this case is then just plug it in. My mass is 95, and I'm going to put it in as kilograms. My velocity is 15 meters per second, and I am going to square that. So when I plug all of that information in, we take our 15 and we square it out, multiply that by 95, and then cut that in half. We end up with 10,687.5. And the units on this are kilograms, meters squared per second squared. I only get to have 2 sig figs, so we're going to round it to 11,000. And the problem specifically asked for joules. But remember, this unit here is equivalent to 1 joule. So we can just swap those out really easily and put this in as a unit of joules. So we have 11,000 joules. Any questions on that? Kind of just a plug and chug. Now, in chemistry, we don't really care about people riding on bikes. We care more about the energy that we find in particles and in compounds. So here is, oh, question. I rounded it to 2 sig figs, David. Yeah, so just refining it to significant figures. So let's look at one that is a little bit more applicable to chemistry. Calculate the kinetic energy in joules of an electron moving at 2.13 times 10 to the 4th meters per second. And the mass of an electron is 9.11 times 10 to the negative 28. There's no caret there, sorry. That's 10 to the negative 28 grams. So similar setup, but the numbers are a little more cumbersome. I'm gonna give you guys 3 minutes to get that one figured out. Definitely want a calculator for that. All right, so we'll be using the same equation of kinetic energy equaling 1/2 mv squared. My mass in this instance is 9.11 times 10 to the negative 28 grams. Now, I know that I need to have my mass not in grams, but actually in kilograms in order to be able to get that joule one-to-one conversion. So the first thing I'm going to do is get grams out, or get out of grams and get into kilograms. We know that for every 1 kilogram, which is what I want, I have 1,000 grams. So I'm going to take my number and divide it by 1,000. So my mass in kilograms will actually be 9.11 times 10 to the negative 31 kilograms. So even tinier than what we had originally. My velocity is in meters per second. So we're already good with that, 2.13 times 10 to the 4th meters per second. So you're always checking, making sure that your units are in the spot you need. So kinetic energy is going to be equal to the 1/2 our mass, which is the 9.11 times 10 to the negative 31 kilograms. And then our 2.13 times 10 to the 4th meters per second, and we're going to square that whole thing. I did have it calculated out, but my calculator cleared it out, so I'll replug that in. I get a relatively small value when I round to 3 sig figs. I'm going to get 4.13 times 10 to the negative 22. And the units on this are kilograms, meters squared per second squared. Again, because...
Did you divide it in half?
Oh, no, I didn't. Thank you, Brittany. Yeah, let's divide that in half. I forgot that. All right. So I'm going to change this guy up here to the, let's go with 2.07. 2.07 times 10 to the negative 22 kilograms, meters squared per second. Now the problem did say, hey, refine it into joules. We can just say this whole clump of unit is equal to a joule. So 2.07 times 10 to the negative 22nd joules. Okay. If for whatever reason this value happened to be in meters per hour, you would want to convert that into meters per second. So when we're looking at thermochemistry, we've got to think about our space as being either the system or its surroundings. So the system, in this case, we've got a piston with a series of gas molecules in it. The system is going to include the molecules that we want to study. So in this case, they're hydrogen and oxygen molecules. They're just bouncing around in there for now. The surrounding environment is going to be everything else. So the cylinder, the piston, the air around this, the universe around it. And we want to be able to separate that because when we're talking about energy, we want to be looking at, is energy flowing into the system that we're studying, or is it flowing out of the system into the surroundings? We've talked about work, energy used to move an object over a certain distance. work here being force times distance. So if we have, if we want to apply a larger force, it'll be more work. If we want to stretch it over a larger distance, again, we'll need to have more work because these are directly related to each other. So as this goes up, this goes up. As this goes up, this goes up as well. Heat, on the other hand, is energy that we transfer from one object to another. The heat will flow from warmer objects to cooler objects. So if you take your hand and you put it around an ice cube, the warmth from your hand will transfer to the ice cube. That would be a transfer of energy through heat. If you were to take the ice cube and throw it against a wall, that would be kinetic energy. So all energy is transferable. When we look at a ball that's placed up at the top of this brick wall, as we move it up from, say, the ground up to the top of this wall, we've used kinetic energy, we've moved it up to the top, and we've stored potential energy in it. As the ball rolls off and then falls off the side, that potential or stored energy is now converted into kinetic energy. And then when the ball hits the ground, its kinetic energy will almost immediately fall to zero. Where did that energy go? Well, the energy will dissipate out in the form of heat. And you probably can't distinguish the heat from a ball dropping, but you would be able to feel the heat from, say, a meteor hitting the Earth at a very fast speed with a very large mass, right? There would be a lot of heat produced. And this process of energy transformation or transferal happens all around us constantly. Kinetic energy can be converted into potential energy and vice versa. Potential energy can be converted into kinetic energy. So we've got a girl swinging. When she's up at the very back or the very front, right at that point where you're like still for a moment, you have an ultimate full pack of potential energy. You're not moving, you're sort of frozen in space for a moment, all potential energy. When she drops down through the center, right in the middle, she's lost all of her potential energy, but she's maximized her kinetic energy. This is where she's moving the fastest. So no movement, picking up speed, fastest, starting to slow down, pause, and then back. Same thing when we look at a spring. We have a lot of potential energy when the spring is stretched, fully extended, or fully compressed. And this potential energy and kinetic energy, this transfer between those two is constant. So the total energy is always conserved. And so that sort of relates to the first law of thermodynamics, where energy is neither created nor destroyed. The only thing that's happening with energy is it's being transferred. And so we can even expand this out to the entire universe. So the universe has a constant amount of energy. If the system or the very specific set of molecules or situation that you're looking at, if that's losing energy, the surrounding environment has to be gaining that energy, right? It doesn't just disappear. The opposite is true as well, and these diagrams are just stating or this in a visual. So if our initial state has a high amount of energy, if it decreases its energy, so say the system decreases to a lower energy state, energy has to be lost to the surroundings. Vice versa, if we have a system that has a low amount of energy and all of a sudden the final state has a much higher amount of energy, that means energy has to be moving into the system from the surroundings, or it's sort of stealing energy from the surroundings. And so this energy that we're talking about, bringing energy in, bringing energy out, we have to talk about this word internal energy, which is symbolized by a capital E. So the internal energy of a system is the sum of all of the kinetic energy and all of the potential energies of that system. So if we're looking at that piston from back, a little farther back here, if I look at this piston, it's the internal energy of this is going to be the kinetic energy of the molecules moving around. It's going to be the potential energy of the bonds of these diatomics. It's going to be the kinetic energy of them hitting into each other. It's going to be the potential energy of the protons next to each other and the kinetic energy of the electrons. It's a very, very complicated number. This internal energy is more theoretical than it is something we can actually calculate. So it's like we know what our internal energy is, but we can't really necessarily calculate it. And by definition, our change in internal energy is always going to be the final minus the initial. So if we have a larger final internal energy than our initial, our delta E should be positive. So when this number is bigger, this will win out from the negative. It will be positive. We'll have a positive E. Positive E, positive change in E or delta E means that we have put energy into the system. If for some reason our final energy is smaller than our initial energy, we'll see that the initial will end up being a larger number. That means that we'll end up with a negative delta E value, which means that energy has been lost or put into the surroundings, or the system has lost energy. So one thing to note, delta E, if it's positive, we're gaining energy. If our delta E is negative, we've lost energy. And that's in relationship to the system. So system will gain energy, system will lose energy. Obviously, it's vice versa. If your E is positive, your surroundings are losing energy. If your E is negative, your surroundings are gaining energy. One thing loses, one thing gains. So here is a diagram that's showing the internal energy. So we're starting here and our arrow is moving in this direction. Okay, so our arrow is moving up, which means that our final energy is higher than our initial energy, or our E final is greater than our E initial. When that happens, we have a positive E value. We're not really talking about numbers right now, we're just talking about concepts. So our delta E in this case, sorry about that. So our delta E is positive here. In this situation, we're going to call this reaction endothermic. Endo because the energy is entering the system, or the system is absorbing energy from its surroundings. It's taking energy from the outside. Low energy to start with, high energy to end with. Well, something has to counteract that endothermic quality, right? Otherwise, we couldn't do it. We need something to be losing energy if something's gaining energy. So if we go in the opposite direction over here, If we're starting at a high energy, at our H2 and O2, and we move down and we form water, our final state has a lower energy than our initial state. That means that we've lost energy, we've lost delta E, or we've released that into the surroundings. In that case, we would call the situation exothermic because the energy is exiting the system. In an exothermic reaction, your product's energy is lower than your reactants, vice versa for the other one. So in our exothermic here, I'll just write it. This is delta E is going to be a negative, and our energy of our reactants is going to be greater than our energy of our products. Okay. So products lower than reactants. So how do we change energy, internal energy? So if we have our system here, which is this little block, and the surroundings is all the white stuff around it, how can I change the energy of the system, whether that's increasing or decreasing? There's two ways that we can do that. We can do it through heat, transfer of heat, or we can do it through work. So here is our equation. So our delta E, or our change in internal energy, is equal to any work that's done plus any heat that is transferred. So in this case, Q is behaving as our heat, and W is behaving as our work. Okay. You do want to know that equation. Pretty simple. Now, the sign is really important on both of those because they tell us which direction they're flowing. So if they're positive, positive heat means that heat is moving into the system. That would be endothermic. Negative Q means heat is moving out of the system. As far as work is concerned, positive means work is being done on the system. Negative W means that the system is doing work on the surrounding environments, or it's losing energy by doing work. So I'm going to skip forward before we do that question, and I want to just look at these in the signs. So again, for Q, a positive sign means that the system is gaining heat. So anytime that we say that the system has absorbed heat, has gained heat, has increased heat, we're talking about a positive Q. Anytime that the system loses heat, releases heat, donates heat, that is going to be a negative symbol for Q. For work, a positive symbol means that work is being done on the system. So the surrounding environment is having to do work on the system. A negative value is happening when the system is doing work done by the system, or it's doing work on the surrounding environments. And then as far as our delta E is concerned, which we've kind of already got this down, but a positive means that there's a net gain of energy. and a negative means that there's a net loss of energy to the system. So we're always talking in reference to the system, not to the surrounding environment. So let's look at a simple problem here. Okay. So it says, calculate your change in E of a gas for a process in which the gas absorbs 20 joules of heat and does 12 joules of work by expanding. And a lot of times work is done through gas expanding. So a system's gas will expand or contract. So we've got to look at this word problem and think, okay, is that energy going into the system or is the energy going out of the system? So in the first case, it says it's absorbing 20 joules of heat. So Q should be a positive 20. Why? Because we're taking that heat on. The second part says that it does 12 joules of work by expanding. So the gas is putting that energy into the surrounding environment. It's losing it. So the work will be a negative 12 joules since the gas is doing work on the surroundings by expanding. So our simple equation, delta E equals, and it's not working for me, Q plus W. Q is positive, so we're going to go with a positive 20 joules. Work is negative, so we're going to add a negative 12. So our overall change in energy will be a positive 8 joules. So it's not hard in the sense that it's just two variables that we're adding together. The trickiest part is going from the word problem, asking yourself, okay, is this energy coming into the system or is the energy going out of the system? Let's do another couple of these. Oh, yeah, I don't want to give that. So if we go down, okay, so let's do this one right here. It says, calculate the change in energy of a gas for a process in which a gas absorbs 55 joules of heat and does 31 joules of work by expanding. And we know from the simple equation that delta E is going to equal our Q, heat, plus W, work. Okay, or heat plus work. Okay, so for this problem, Q is our heat, and this problem says the gas absorbs 55 joules. So 55 joules, and I'm going to give that a positive value because we're bringing that heat into the system. We're taking it on. Our W, our work, we've got 31 joules. As far as the sign is concerned, it says that it does the work. So if it's doing the work, it's giving that up. So we're going to make that a negative. So our value here of delta E should equal a positive 55 joules plus, in parentheses, a negative 31 joules, for an overall delta E of 24 joules. Any questions on why this one's positive and that one's negative? Okay, I'm going to have you do one more. So this one here says calculate delta E of a gas for a process in which a gas produces 76 joules of heat and has 132 joules of work. Let's change that to work. Done on it. Okay, so for this one, let's figure out our Q and our W. So Q is heat. So here's our heat. It says it produces that much heat. So we're releasing that heat to the surrounding environment, 76 joules, and this is going to get a negative value, negative 76. It has 132 joules of work done on it. That means that the surrounding environment is putting that work into the system. So the second value should be positive here. So delta E is going to equal a negative 76 joules. 76 joules plus a positive 132 joules. So we end up with a net difference of 56 joules. Any questions on how to do those? Could be combined in a bunch of different ways. Well, you know, there's 4 different options. We can either take the heat on, we can release the heat, we can have the work done, or we can do the work. Okay, but always be calculating it from the seat of you are in the system, not in the surrounding environment. So we've already gone over this, but When heat is absorbed by the system from the surroundings, the process is, we would classify the process as endothermic. So if heat moves into the system, endothermic, the heat is entering the system. If you've ever used one of those like cold packs that have, it's like a chemical bag full of chemicals, and then there's a little bag in the center and you have to break it and then it gets cold almost instantly. That is an endothermic reaction. So what's happening is that the materials within that system are drawing heat from the surrounding environment. So then you put that ice pack on, you know, say a swollen part of your body, and it will pull heat from the body. When heat is released, we consider that to be an exothermic reaction. So if I pour two things together and I have a thermometer sitting in there and all of a sudden the temperature on the thermometer spikes, it's because heat is moving from the system into the thermometer to raise the temperature of the thermometer. So as far as our internal energy, we classify internal energy as a state function. We don't really have any way of calculating the internal energy of a system. It's just too complicated. Let's say we have this beaker of water here and it's 50 grams of water and it's at 25 degrees Celsius. It has some sort of internal energy to it, combining any sort of kinetic movement energy or potential energy within the bonds. But it's a really, really complicated thing to take into account. So we don't actually know that value. But one thing that we do know about the internal energy of this system here is that it is independent of the path at which you achieved that state. So that is what a state function is. A state function depends on the state of the system at the current moment. It doesn't depend on the path in which it took to reach this place. So if I say started with a 50-gram sample of water at 100 degrees Celsius, and I cooled it down to 50 grams at 25 degrees Celsius, this state is going to be the exact same as if I had freezing cold ice cubes, 50 grams of it at 0 degrees, and I raised the temperature. The path at which you enter to this doesn't matter. That is what classifies it as a state function. Could have reached it from any direction. I could have had a sample of water that was at, you know, instead of 100 degrees, it was at 93 degrees. And again, it wouldn't matter as long as it enters this place. They all will have the same internal energy. We don't really know what that internal energy is because it's really complicated, but we do know that it is in fact the same. So because of this, because it doesn't matter what path it takes, we classify it as a state function. Depends only on the present state. So if this is where we are in the present moment, that's the only thing that affects the amount of energy it has. And so because of that, delta E, our value will only depend on our initial and our final. It won't depend on any sort of side steps, or we kind of think of it as only looking at the net change in energy. So here is an example of a state function. And just so you know, Q and W are not state functions. So Q, which is heat, and W, which is work, do depend on the path that you take, okay? But if we look at this here, we can see this as a state function. So I've got a battery, and it's a charged battery. So it's sitting up, if we look at this as our energy, right? On the left, I am just short circuiting the battery. I'm just connecting it to a wire. On the right, I'm actually putting it into a system where there's a fan, and the fan is producing some sort of kinetic energy. On the left, when we're just discharging the battery, all of the energy lost is going to be through heat. So as it moves through this coil here, it will produce 100% of the energy lost will be produced through heat, and the battery will be discharged. On the right, the battery is going to lose some energy through heat, but some of it's going to be lost through work or producing a force over a distance in the fan. Either way, though, whether we lose it all through heat or we lose it, through heat and work, the total difference is still the same. So whether the battery is shorted out or it's running the fan, the delta E is still the same, or it still has that state function quality. The end result is the same. But these within there, the heat and the work themselves, are not state functions. All right, so when a process occurs in an open container, commonly the only work that's done in these chemical reactions is a change in volume of the gas, or the gas is pushing on the surrounding environments. And so there'll be some sort of, like here we have a piston, and if there's work being done from this gas on the surrounding environments, will increase the volume and it'll push around. So we can measure the work done by a gas using this simple equation here. So work is going to equal the negative pressure times the change in volume. So the larger the change in volume is, for instance, here we've got a situation where we take zinc and we have hydrochloric acid, and we pour the zinc into this system. It combines with the hydrochloric acid and it starts to produce gas. The gas will then expand and it produces work, which will be, we're saying that the gas is working on the surrounding environments, or it's doing work, because the piston is being pushed up and out into the surroundings. So it'll be a negative value. That's why there's a negative there, because the system is losing some of its energy. The system is losing some of its energy through work or by pushing the piston out. So the greater volume, let's say we produce more gas, the more work that's going to be done, or the more work that will be lost by the system. So again, the energy of an object depends only on its current condition. The current condition is called the state. Internal energy we classify as a state function because it's a measure of energy. An important property of state functions is that they are independent from the mechanism or method which allowed the change to occur. So again, a state function is really, we're only looking at the current present state as opposed to how it got to that place. We've already talked about this, but the object we are interested in is called the system. Everything around it is called the surroundings. There's a boundary that separates those two from each other. If we take the system and all of the surroundings and we sum them together, we get the universe. And then systems are classified according to what can cross over a boundary. So what can go from the system to the surroundings, or vice versa. So when you hear someone discussing an open system, in an open system, you can gain or lose mass and energy. So if I have an open system, I can change or transfer energy, and I can also transfer mass. So we could, put heat out. We could also lose some of the material that we have. When we're dealing with what's called a closed system, we can absorb or release energy, but we can't transfer mass. Okay, so that situation with the piston, where we had the gas molecules in an enclosed container, we would say that that's a closed system. We can transfer heat and energy, but we can't let the gas won't release. In an isolated system, we can't exchange either energy or matter or mass to the surroundings. So the sign of heat change is used to say whether we're gaining or losing heat. We've already gone over this, but when heat is gained by an object, we give it a positive number. When heat is lost by an object, we give it a negative number. If we say that there's some sort of spontaneous change, it's a change that occurs on its own. One of those examples of spontaneous change is heat flows spontaneously from warmer to colder objects. Also, pressure moves from higher to lower pressure environments. Okay, so I think we'll stop there for today. We'll get into enthalpy next time. So we've got a little bit more background stuff talking about enthalpy. We won't be doing a whole lot with these equations. And then we'll get into some actual math stuff. Okay. So you are good to go. If you have any questions, feel free to stay around. Otherwise, I will see you all on Thursday. All right. Bye, guys.